Roots and powers 3, mixed and entire radicals. Recall, which is just a fancy word for remember. A radical, oh, get my pen going here. A radical is the combination of an index and radicand. And another word for radicand that you'll see maybe in your grade 12 or whatever is called an argument. It's underneath the squiggly of a root sign here. So we know that the square root of 81 is plain old 9. But, and the implied index here, just remind yourself, recall. The, the implied index here is 2, but what happens if I put a 4 here? The index is 4. The 4th root of 81, that means what number do we multiply 4 times to get to 81? Well, if I go 3 times 3 is 9 times 3 is 27 times 3 is 81. So that means that the 4th root of 81 is simply 3. So that is an entire radical, okay? There are no numbers kind of out in front. We have an index, we have a radicand. However, a mixed radical has a number in front of the radical. For example, I would have something like 2 times the 4th root of 81, like that. And usually mixed radicals, the argument and stuff like that cannot be simplified any further. So just for my brain, I'm going to put a 3 there instead of a 4, because I know that the 4th root of 81 can simply just be simplified to 3. So simplifying radicals can be a little bit daunting, but I think that the good work that you did in your other notes will help you with it. So when simplifying radicals, we want to write an equivalent, so that means the same, but it's a fancy math word, equivalent, form of the radical using smaller numbers. So method 1, prime factorization. So the question here is simplify the square root of 60. So simply rewrite the radicand. So remember the number that's underneath the radical sign as a product, so multiplying, of its prime factors. So when we do that, I'm just going to zoom in just a little bit further to give me some more room. The square root of, the square root of 60 is going to be the same thing as, say, something like 6 times 5 times 2. So then I can split that 6 down further. So I can say 3 times 2 times 5 times 2. And I'm just doing this in so many steps, just so you can see exactly what I'm doing. You can cut it down to a smaller number of steps. Now usually I go in ascending order. So I have 2 2, so 2 times 2 times 3 times 5. That's our prime factorization from lowest to highest. So then group the factors. Group the factors in clusters indicated by the index. So remember, if it's a square root of 60, the implied index is 2. So we need to find numbers in groups of 2. So when I look at this, I'm going to say the square root of 2 times 2 times 3 times 5. I only have one cluster of 2, and I'm just going to highlight it right here, this guy right here. Boop, boop. Come on, buddy. Oh, it doesn't want to do that for me right now, but that's okay. You get it because it's in brackets. So remove the clusters from your radical. So remove the clusters from your radical. All right. So I'm going to say 2 times 2. I like to split it kind of into the clusters out like this. So the square root of 4 times the square root of 3 times 5, like that. I can simplify this square root of 4. I can call it a 2. 2 root 3 times 15. And because I don't want to have a math question in my answer, I can simply simplify to 2 root 15. And put a box around your answer because I like my teacher. Okay, so method, it's not actually method 1, it's actually method 2. I'm just going to change this right here. So the second method that we can use, so if you like this way, that's great. I'm going to show you a different way. Greatest index factor. So same instructions. Simplify the square root of 60. So first step first is factor your radicand. And to figure, like, to factor your radicand, you just write out what all the factors are. So I can multiply 1 by 60 to get to 60. 2 is a factor, 2 times 30. 3 times 20. 4 times 15. 5 times 5 times 12. Hello. 6 times 10. 10 times 6. 12 times 5. 4 times 15. 3 times 20. 2 times 30. And 1 times 60. So these are all the factors. But the question that we need to look at, we look through this guy right here and we say, which is the greatest perfect square? And we're using square because our index was 2. So the answer to that one, when I look across here, let's see if it'll work this time. I'm looking. No, it's not liking my highlighter. Oh well. My biggest perfect square in the whole thing is going to be 4. So 4. So rewrite your radicand as a product of 4 and 15, because 4 times 15 is 60. So very similar thing, 4 times 15. And I really like to split it off into 2. So the square root of 4 times the square root of 15. I can simplify this. The square root of 4 is just simply 2, so it's going to be 2 square root of 15, like that. Put a box around your answer, because I like my teacher. Okay, now let's bring out the big guns here. simplify the third root of 40. So we can do the prime factorization. So that means that write out all the prime factors. So if I'm going to say the third root of 40, how do I get to 40? And I can take a few steps to get here. 40 is just 4 times 10. Now I can simplify this even further here. 4 is 2 times 2. And 10 is 2 times 5. And because I have an index of 3, I'm looking for groups of 3. And looky there, I have 3 2's. So that means that outside of the radical, like if I separated it out, the third root of 8 times the third root of 5, I can simplify this into a whole number. My whole number in this case is going to be 2, because 2 times 2 times 2 is 8. So that means the third root of 8 is 2. So I have 2 third root of 5. Okay. Another way that I can work on this one is, it's maybe helpful to show a prime factorization chart. So that's what this would be, prime factorization chart. I would say 40. It's just going to be 2 times 20. But I can split this guy right up here. I can say 2 times 10. And I can split this guy into 2 times 5. Okay. So then your prime factorization will just simply be this, which we get right here. Okay. But the prime factorization tree is actually a really helpful thing. So this is method 1, using prime factorization. If you wanted to use finding the biggest perfect cube factor, I'm just going to write down my perfect cubes, but you can just look back in your notes because you've done this already. 1 to the power of 3 is 1. 2 to the power of 3 is 8. 3 to the power of 3 is going to be our 27. And 4 to the power of 3. 4 times 4 is 16. 16 times 4. Oh, I have a brain fart. 16 times 4. Oh, my gut said 24. I'm so sorry, everyone. Even math teachers who do this all the time have brain farts. So I know it can't be bigger than the thing I'm trying to factor here. So when I look at this, I'm like, ooh, 8 times 5 is 40. I think that my biggest, if I write out my factors, so 1 and 40, 2 and 20, 3 and nothing, 4 and 10, 5 and 8. I think that these are all my factors. If I look at it, my biggest perfect my biggest perfect cube factor is going to be 8. So I'm going to say the third root of 40 is simply the third root of 8 times the third root of 5. But I can simplify this one down. I can simplify that down to 2, because the cubed root of 8 is going to be 2. So it's 2 cubed root 5. Same answer. Okay, just 2 different methods, and depending on how your brain works, it works better. It works better one way for you. Okay, now going the other way. Let's try this. So writing mixed radicals as an entire radical. So we're going to simplify 3 root 5. So simply rewrite the number outside the radical. So rewrite the number that is outside of the radical as a product of the index. Okay, so we're gonna unpack that a little bit. As a product of the index. Okay, so I'm saying 3 root 5, but I like to think of it as what does it look like when it lives underneath the radical? Well, 3 in the outside world is 3, but under the radical, it's 3 times 3. It's going to be 9, okay? And then multiply that by 5, okay? So all I'm saying is 3 is the exact same thing as the square root of 9. Okay, so underneath the radical, it's going to live as 3 times 3, or 9. Out in the wild, outside of the radical, it's going to be written as 3. Now combine the radicand, or argument. So 3 times 3 is 9, times 5 is 45. So as an entire radical, see, we went from mixed to an entire, because I have a whole number out in front and a radical. Now we just have an entire radical. So we moved from mixed radicals to entire radicals. Okay, what happens if I have a bit more of a spicier, a little bit more of a spicy index? Let's try it out. This is actually a lot easier than going the other way, because we don't have to know what our perfect fourth numbers are. I can simply write the mixed radical as an entire radical. So that means that everything in my final answer is going to be under the fourth root. Okay, so I have 2 and the fourth root of 5. The fourth root of 5 is fine, but I have an integer here, or a whole number here, living outside of the radical. What does it look like when it's underneath the fourth root? Well, I'm going to say that it's 2 times 2 times 2 times 2. Then I need to multiply the fourth root of 5 to that. Okay, so 2 times 2 is 4, times 2 is 8, times 2 is 16. So, I mean, another way that we can just have a little bit of side work here, the fourth root of 16 is simply 2. So when it lives under the radical, the fourth, with an index of 4, it's the fourth root of 16. But when it lives outside of the radical, it's just simply 2. So now we have the fourth root here of 16 times 5. 16 times 5 is just 80. So we've gone from a mixed radical with a whole number outside of the outside and a radical to an entire radical. An entire radical lives entirely under the radical sign. I don't know why I found that so funny. Okay, so your textbook work is on page 218, and the questions are indicated in your notebook.